Hello, the name of a project is Nash Equilibrium and Alternatives to Asymmetric Information Constant Sum Game. We are Group 15 from CS 5446 AI Planning and Decision Making. I am Saurabh Singh.
I'm Nishita Datta.
I'm Vaishnavi Mena.
To start off, we all know that each and every game has a number of decisions that a player has to make and a number of strategies which he or she can follow in order to get a payoff, which in simple terms could be a reward. So here in any game, what is a Nash equilibrium? Nash equilibrium is a concept within game theory where the optimal outcome of a game is where there is no incentive to deviate from the initial strategy. Overall, an individual can receive no incremental benefit from changing actions, assuming the other player remains constant in their strategies. A game may have multiple or none at all, none equilibriums at all. In this project, we have implemented the same in non-cooperative games. In game theory, a non-cooperative game is a game in which individuals compete with each other. In a non-cooperative game, the agents cannot reach a binding agreement. This game has winners and losers in each case, and it could also lead to a draw. The best example for this is a rock paper scissors game. In this project, we have discussed Nash equilibrium and two other models as an alternatives to it, which are belief based and reinforcement based. We have studied three papers. The first of which is game theoretic approach planning, which was published in year 2015 by Jordan and Eva. The objective of Nash equilibrium here is that we have to predict whether there is a Nash equilibrium present in a multi-agent game or not. The game was described in the paper in 2007 by Larby and Mark Watts. The general game which was implemented in this paper can be seen in the table. The environment is set up in such a way that there are set of plans for each agents being A and B, and they are set to go through two problems, and the number of actions in each plan and its utility is given in the table. And player A and player B both can perform actions being denoted by pi subscript the name the number of the number of action and the name of the player as pi A1, denoting that it would go on to reach goal 1 and goal 2 by playing three actions, and its utility can be defined by the formula given as the number of goals multiplied by 10 and minus the make span, which basically denotes the delay in the action. Since the player can also choose to not perform an action which can cause the delay in their during their trial of play. The results of the utilities can be found in this table, which have been calculated using the tool called Gambit. We know from the Nash equilibrium that we can find it in a payoff matrix in the formula using the fact that the first number in the payoff in the cell should be the maximum in the column, and the second number should be the maximum in the row. Here we can see that the action denoting pi A1 and pi B1, which is the first cell itself, is the Nash equilibrium here.
The second paper that we have considered is Beyond Nash Equilibrium Solution Concept for 21st Century. This paper mainly describes about the shortcomings of Nash equilibrium and try to, in computer science perspective, and provide some solution concept that try to address these issues. So first one is Nash equilibrium does not tolerate unexpected or faulty behavior. So Nash equilibrium can tolerate deviations up to one player, but it cannot tolerate deviations more than that. Or if they are deviating in a coordinated way, then the Nash equilibrium can tolerate. Now, a solution to this is to consider Nash equilibrium as a KT robust equilibrium. That means it should be K resilient and T immune. K resilient means if it tolerates deviations by coalitions up to K players, and T immune if non-deviators do not get affected or hurt by the deviators. Now let us consider an example where there are n bargaining agents sitting around a table, and if all of them stay in bargain, all will get a payoff of 2, and if one leaves, the person who is leaving will get a payoff of 1, and the others will get the payoff of 0. In this case, we can say that it is K resilient because it is tolerating the deviation. but we can't say that it is T immune because the non-deviators are actually getting affected by the deviators. In such a scenario, we can make use of a mediator, a third party, who would help to make it a T immune. So this next issue is Nash equilibrium does not consider computational cost into account. Now let us consider a n-bit prime number as shown here. Now, the player has to guess whether the number is prime or not, or can say nothing. If he's correctly guessing, then he get a payoff of +5. He guesses wrong, then he get a payoff of -5. If he says nothing, then he get a payoff of 1. Here, the Nash equilibrium is getting a payoff of +5. But since his number is very large, we need a computer algorithm along with the computer to write a program and figure it out. So this means we need a computation cost. So a solution to this, first solution was to use a finite automata. But even by using finite automata, there might be scenarios where there will be more number of states and which would lead to using more computational cost. Second solution was to use a Turing machine. So a Turing machine is basically a hypothetical machine which could simulate any computer algorithm, no matter however complex it is. So now let's consider another example of finitely repeated prisoner's dilemma. So here there are two actions, that is either to cooperate or to defeat. Here the Nash equilibrium, they have experimented and they have set it as to defeat. So while using the finite automata and Turing machine, they found that they're always cooperating each other. So in order to reach the Nash equilibrium, they use this tit-for-tat strategy where each player takes an action based on the action taken by the other player in the other round. So here the memory required to store is very less. Just need to store the action taken by the other player in the other round. So hence the computation cost will be also less. Next one is Nash equilibrium always believes that players are actually aware of all aspects of the game. But in real game, it is not the case. Now let us consider another example. There are two players A and B where they have two actions, across A, down A, and across B, down B. So here the Nash equilibrium is considered to be across A and down B. But now suppose we say that A is not aware that B is going to take down B. Then A will take down A. In that case, it won't reach the Nash equilibrium. In such scenario, we need to consider a game as an augmented game, then which is an extensive game plus one extra feature. So what is an extensive game? An extensive game is a game where you represent a game in the form of a tree, where each node will give you the information about the player and all the actions that led to the node. And if we add an extra feature which will have all the history about what other player has done, then it will become an augmented game. So this augmented game will help us to resolve this issue of lack of awareness. So these are the three issues of Nash equilibrium when we consider in a computer science perspective.
Our final paper is reinforcement-based versus belief-based learning models in experimental asymmetric information games, written by Nick Feltovich. This game theory helps economists predict behaviors of people when they are in conflict or with opposing interests to those of their opponents. The objective of this paper is to analyze if we can predict player behavior in a game that is asymmetric, as in the form of information that the player has in his game environment is not equal. That is, some players may have some incomplete information to play the game and must make their decisions to the best of the knowledge given to them. The authors assume that the players make decisions based on a learning model. That is, with every round of the game, they adjust their strategies. He examines the efficacy of Nash equilibrium, reinforcement-based learning models, and belief-based learning model in predicting the approach of the players. Experiments were conducted with 200 students who were asked to play a two-player game with an asymmetric information situations. It is assumed that all these players would be rational and not make any decisions on any whim, as they are incentivized for playing the game optimally. It is seen that Nash equilibrium of the game was not very suitable to predict the behaviors of the players. That is, the players did not make moves that were in line with the equilibrium of the game. Whereas the reinforcement-based models and the belief-based models were more in sync with the actual player behaviors. In the reinforcement-based model, much as the name suggests, the players learn according to the payoffs they received in the previous rounds. In the belief-based models, players formed guesses or some preconceived notions about their actions of their opponents and played accordingly. Both these models were compared, and it was seen that they were both able to predict player behavior with almost the same accuracy. We wanted to find out if these models are actually a good way of beating the game, and given a real situation, would these models actually pay out for the players involved? We simulated all three models using a computer program for playing the game and analyzed our findings. So the game consists of two payoff matrix, two players who are given two actions A and B, and a constant sum reward in each round. Every round of the game consists of two stages. A game G of P is a game in which the left matrix is chosen with a probability of P and the right one is chosen with a probability of 1 minus P. The player 1 is aware of which matrix is chosen, whereas the player 2 is not given this information. In stage 2, however, the player 2 is told which action the player 1 took. Looking at the actions of player 1 in round 2, player 2 can make an informed guess about which matrix is chosen and play his action for the second stage accordingly. The dilemma here for player 1 is how much to reveal to player 2, and so that he wins the second stage. And the dilemma here for player 2 is how much to trust the action of player 1 in being his stage, that the action that the player 1 played is a stage dominant action in stage 1. This situation can be aptly described as a scenario where I know what she knows that I know that she knows, and so on and so forth. We'll refer to the stage dominant action P of player 1 as P of SDA when player 2 takes an action of action A in the left matrix and action B in the right matrix. The player 2, if he assumes that the player 1 has completely revealed the matrices to him, that he assumes that the stage dominant action was played in stage 1, then he plays a suitable response to it, then this will be called as the best response to completely reveal it, which is action B in the left matrix and action A in the right matrix. What happens is that when the player 2 plays action B in the left matrix and action A in the right matrix, player 1 loses all chance of ever winning in the second stage. And anyway, in this first stage, he can only win with a certain probability. So it is almost as if player 1 never had any extra information to begin with, which is why player 1 needs to form a suitable strategy to get maximum payoff from any round in the game. Next, we'll understand the Nash equilibrium for this game along with the two learning models that we simulated to play the game.
So for the Nash equilibrium part, here we know that the stage dominant action for player A, player 1 is A in the left matrix and B in the right matrix, and accordingly the best response that player 2 can give is taking B in the left matrix and R in the right A in the right matrix. It is a mixed strategy Nash equilibrium. From Nash's theorem, we know that if no equilibrium exists in pure strategies, then one must exist in the mixed strategies. There is a probability distribution over pure strategies here. That means that player chooses randomly or with some probability among the options in the equilibrium. If mixtures are mutual best responses, then the set of strategies in the set of strategies is a mixed strategy Nash equilibrium. By playing mixed strategy, player 1 plays randomized actions to confuse the other player. The following table shows Nash equilibrium predictions obtained by taking different values of P. From the simulated 200 games, taking the value of P to be 0.5 and 0.34, we can see from the results that the average payoff or the expected payoff converges to a value when the initial strategies were defined beforehand for each case, hence showing that these strategies of taking actions constitute a Nash equilibrium. This equilibrium is not unique as there can be more than one present depending upon which matrix is chosen.
In the belief-based learning model, we assign some prior belief about what we think the opponent might play. And then in the subsequent rounds, we update our beliefs. So we update our beliefs for every action as 1 minus delta into the belief of the previous action added to 1 if the action was played by the opponent. And if the action was not played by the opponent, then we do not update our belief. The probability of our opponent playing this action is then calculated as a strength of our of the current beliefs. Here, delta is the parameter that decides how relevant our past beliefs are in constituting our current beliefs. For example, if we look at the complete extremes, if delta is 0, that means our past beliefs were completely relevant and we just add onto a unit value for the current belief. If delta is 1, that means our past beliefs have no relevance at all, and we update our beliefs with for every round with a new unit value. Next, we calculate the beliefs as a percentage of the total strength of the actions that the opponent might have played. Given these probabilities, we can calculate an expected payoff or utility for playing each action in the stage, given that the opponent played the actions with the given probabilities. The probability that the player chooses the best response or the pure strategy S is given by the following formula. The parameter lambda determines the extent to which the player responds optimally to her beliefs. If lambda approaches 0, it means that she chooses the action A or B with equal likelihood at each information set, irrespective of the expected payoff. As lambda gets large, her strategy more approaches the best response play.
The reinforcement model that we have considered here is a Roth and Irv model, which was developed in 1995 and 1998. So here, an action is taken by the player is based on the propensity. So from propensity, we'll figure out a probability, and from based on the probability, an action is taken by every player. So initially, the propensity should be we have taken as a random number between 0 and 10. And after each round, we need to update the propensity. So the updating of propensity, now let us consider in our case, we have two actions A and B. So if player 1 in round T is taking an action A, then in round T plus 1, its propensity for action A gets added with the payoff for round T, and B remains the same. Now, from propensity, we have to find out the probability. The probability of taking an action for a particular player is the propensity of that particular action for the particular player divided by the strength of propensity. Strength is the sum of propensity for playing both the action. Now, based on this propensity, and the probability, an action is taken by every player in our game.
We simulated the game for 200 episodes with 40 rounds each and plotted the probabilities of player 1 playing his stage dominant action and for player 2 playing the best response to a completely revealing player 1 for every learning model. We analyzed how the gameplay changes when any of the players start playing their stage dominant action, and if or not, they converge to the Nash equilibrium of the game. For the belief model, we selected different parameters of delta, lambda, and p and simulated the game. Here, we see that the probability of the players choosing their stage dominant action or BRCR fluctuate between the equilibrium points. That is, they lie between 0.4 and 0.57. There are peaks and dips throughout the game because the game is a constant battle between bluffing or not bluffing for player 1, and for player 2, it's a decision he needs to make about whether or not to trust the action played by the player 1. Playing any one strategy for a long amount of time results in the opponent to start learning this behavior and acting in a manner that is not conducive to this strategy. Therefore, the opponent needs to change his strategy, and the probability with which his actions change keep increasing or decreasing. This goes on, and even though the values are close to the Nash equilibrium, they never converge. This is in line with the findings of the paper by Nick Feldovich, who also says that the models make predictions that are qualitatively similar, cycling around the Nash equilibrium, then that is much more apparent than movement toward it. Our observations for the reinforcement model were also quite similar, and the graph is of a similar nature, we might start out with different initial propensities, but eventually the graph assumes a similar trend. It is important to note, however, that the players using this model are only motivated by the payoffs they receive, and they do not care much about the actions of their opponent. Hence, there is a larger overlap of the probability of stage dominant action with the probability of best response to completely reveal. The other experiments that we conducted were to simulate gameplays with different learning models or with agents that had a different learning model than the other. We also changed the initial beliefs, initial propensities, and parameters like delta and lambda. Future work on this could include choosing a more balanced payoff matrix, as we know that this payoff matrix is more inclined to reward player 2 and instead of player 1. So we could choose a payoff matrix that is more rewarding to player 1 and observe how these models are able to predict behaviors of the players, and also possibly design a different learning model to sort these changes.
Next, the question arises whether this reinforcement model or belief model address the issues with Nash equilibrium. Now, if you consider, if any player deviates in reinforcement or belief model, then it doesn't affect the other player. So the issue of fault tolerance or unexpected behavior is not there, is not present up to a level. Now, the computational cost required to find the updated belief or updated propensity is not that high when compared to the computational cost required to find a Nash equilibrium. Then players are actually not aware about the all aspects of the game. But let us consider the belief model where in each stage action taken by the opponent player is passed. So hence it is not fully not aware about all aspects. So the issue of lack of awareness is also resolved up to a level. These are the references that we have used throughout our project. And we hope our presentation was insightful, and thank you.